I think we're going to begin. Yeah, cool. All right. Yes, that's correct. We are going to begin. Good afternoon, everyone. Welcome back, B-Sides. Whose pipeline is it anyway? If you're too young to get the reference, I'm not sorry. In improv, it's like AI can't spell. That might be like the new Turing test, we're not sure. And if you're too old to get that joke, I'm still not sorry. So, hey, I'm Matt.
And I'm Zach, everyone.
We are staff security engineers at a company called Dutchie Inc. I focus primarily on application security.
And my focus is infrastructure and cloud security.
But we work really closely together in kind of all aspects and the ins and outs of our day jobs. So we do these things together.
Quick disclaimer, our views are our own and not representative of any current or former employer. We got that out of the way.
Great, so why are we here? Why are you guys here? What are we here to talk about? So we actually do a lot of threat modeling. And in kind of preparing for this, like I focus a lot in the weeds on application security, and Zach was like, hey man, like it's time that we actually do, like we need to take a look at our infrastructure and look at CI/CD and like look at our pipelines and things like that. And I said, okay, you're right. And then we saw a lot of the other research that was coming out and around in the space, and we looked at each other and we were like, oh yeah, we do need to look at this. So because of those emerging trends and because we wanted to transition and start looking at our infrastructure and do a threat model of that, that's basically why we're here. So to emphasize on that, the core feature of this talk really is threat modeling and then threat modeling of CI/CD. And so then to do that, we will build a CI/CD pipeline, kind of walk through the structure of it and its purpose, and then we'll start to formulate like the attack trees and threat models. Some of our attacks will be based on some of that research that we saw, and it will be like real world scenarios, or try to get, we're threat modeling, so it's a paper exercise, but we're going to try to bring in as much like applicability to it as possible. So with that, we're doing the CI/CD of threat models. This talk is not specifically how to threat model. It's not a threat modeling workshop. But if you've never done a threat model before, there still should be something here for you. And if you're like, oh man, I'm threat modeling CI/CD next week, there also should be something here for you. So the last thing, is this different from the body of work that's out there? I don't know, but I like to believe that it is, and we hope we can kind of workshop that with you. Some of the things that we're doing that we appear to be different are like we have the weaknesses that manifest into attacks on the threat model in the attack trees, and so that might be something that's of interest to you to take back to some of the things that so before we get into anything else that's threat modeling related, let's talk together about what is CI/CD.
Yeah, so like Matt said, before you even start to try to threat model the environment, you first need to conceptually understand what a CI/CD pipeline is. And essentially there's two converging ideas that are taking place that conceptually start to form a pipeline. And there's two lines of thinking, two ideas. One is continuous integration, and the other is continuous delivery or continuous deployment, depending on how mature your processes are. So those are best encapsulated via the orange highlighted areas around the workflow here. And now if you click.
Sure. So continuous integration is really more so followed as like a practice or a process, really more so than like, this is the system or the tool that you're going to use. So you kind of keep that in mind, and that also makes this like more applicable to what you might be doing in CI/CD, but there's different parts that you can like plug and play and bring in and use. But ultimately, the CI, the continuous integration portion, is getting your developers and their code into production as seamlessly as possible. The CI part is like the source code repositories, the building application process of that, where it's packaged up and then handed over to the delivery and deployment.
Yeah, so the next phase is, like I said, either continuous delivery or continuous deployment. Once there's actually a functional release candidate, this is the next phase of the pipeline. It focuses on automating the release of approved code changes to a repository. The goal is to ensure a rapid, reliable, and repeatable deployment process. There are a fairly exhaustive list of CI/CD benefits out there, 3 of which are here on the right: the quick feedback loop, the enhanced collaboration between developers, and also the increased engineering velocity. The ability to push code frequently and often is often the term that's used.
Great, so here is we're going to build this CI/CD pipeline together. This is a pretty accurate representation of what you might be using, or your teams might be using, or someone somewhere in the universe might be using. Regardless, this is a functional CI/CD. So, going back to what the CI components are with this, so we have the developers, and essentially in like an ideal world, a customer, whoever that is, whether like it's someone that pays you or it's like a development team that you're trying to get tools to, they would manifest an idea in their brain, then the developer would think it, and then it would just be running in production. That's not actually how it happens. We have to like build the thing together to get there. And so we have the CI pipeline to do that. So it starts with like your IDEs, your developers, what the tools that they're using. Here, this then gets pushed into a VCS, version control system, and then this is where the code lives. And then the code lives in its various different forms. You have your applications and your products, and then you have your infrastructure as code, you have manifests and scripts that are helping the build process and kind of instructing the other facets of the CI, getting the build and your artifacts together. So there's triggers in there, so these things can happen automatically. They can be responsive to what type of code you have in there, but it also can be something manual. You can have like a gated flow process of, hey, great, we're in the source control system, but I don't want you to build yet, and I certainly don't want you to deploy yet. So we have these configurations and rule sets to talk about what are the next steps to take, or you can just automate all of that and forget about it. Your secrets live here, and then we talked about your YAMLs and your manifests, like other instructions on how to build. So once you do get to that point, you say, hey, let's turn this code into the binary or the container, then it gets passed off to the build server. So in the build system, we're talking about GitHub Actions here, but this could be your Jenkins, it could be your Circle CI. You go into the build, and so now we're actually talking about compilation, we're talking about building, we're talking about getting a binary and an image together that's ready to be handed into the delivery phase. GitHub Actions will also allow you to like start doing your static code analysis, and you're creating the artifacts that ultimately become the things that get pushed up. So now we're getting passed over into the artifacts. This is kind of similar to your source code repository, but it's a container registry, or it's an image registry, or an artifactory for your dependencies and your binaries. You put your image up there, you give it a tag, you give it a label, maybe put some rule sets around it, and then ultimately we're going to talk about like the environments, but you have a development image, you have a production image, and then there's processes that can happen that promote the container into being like, hey, congrats, you're not in dev anymore, you're prod, and so this gets built into that build system. So now that the image exists, it's packaged up, you have your container and your binary, now we start doing delivery and deployment.
Yeah, so the continuous delivery portion, you can click next one. It's highlighted in the orange box here. Like we were saying, we have one physical pipeline with two converging ideas, one with continuous integration, one other with continuous delivery. That doesn't mean there's like a perfect segue from where one thing's end and where the next begins. So once there's a functional release candidate and you're sitting there with artifacts that have been tested by the development team, it's ready for orchestration, which sets up to get ready to deploy your application onto a modern environment such as Kubernetes. So that's best dictated by the Argo CD layer as well, and then it essentially controls the applications in the lower environments as well as the production environments. So within the Argo CD environment, it leverages a principle called GitOps, which essentially leverages GitHub as the source of truth. And then from there are many pods that are sitting there in clusters holding your application. It does an apt diff against the GitHub repository that's actually storing the code, and that's best dictated by the repository server that you can see the flow goes into GitHub, the source control management suite, and then feeds back, and then from there it moves upstream to the application controller, which then is able to deploy your application to various environments. So that is the actual orchestration, but with that said, there's also a production environment that hosts your infrastructure as well, and that's best indicated by the sub-bullets under each respective area, such as networking, infra, OIDC for anything, authentication, and the EKS and storage environments as well. Benefits of GitOps, it's auditable, it's version controlled, it's increased reliability, it enables you for rollback, so you can deploy a service if something quickly breaks. You can essentially just use what's essentially a git revert command, and then you can move back to the previous known stable build. So it's very scalable to that point as well. Many different developers, once you abstract your application, are able to iterate on their code independently of other pieces of your application.
Cool. How many people threat model here? Yeah, good amount, all right, we're doing stuff. We threat model too, and so we have our approach to threat modeling. Ideally, from our perspective, threat modeling is a highly interactive and highly iterative process. I think for this exercise, Zach and I did really well in the highly iterative part. I think we could be a little better with our interactive part. But anyway, when you're kind of starting to sketch this out of like what you're going to do, you know, I'm gonna laugh at myself when I say this because like I'm sure everyone here in this room hears shift left a lot, and you're like, but small scope user stories is like the shifting left of threat modeling. It's like, hey, there's only so many people in this room that can do threat modeling. We need to get our developers threat modeling, and if you're developing user stories and like having agile frameworks and doing stuff like that, if you just give them a few tools and the mindset of like attacking their own little user story, you know, that's shifting left and like getting them to kind of have buy-in and help us out in what we're doing. And then there's large scope, so that's like, hey, we have a giant framework, there's this huge architecture pipeline, we need to kind of threat model this whole thing. You could do it in like each stage of the pipeline, but it also kind of makes sense that while you have the engineers and the developers and their attention and the resources to do the large thing. And so, you know, we're balancing in these worlds. And then all of this is not to be demanding on engineering. I know that, you know, we're building cycles for them to work on backlogs, to do threat modeling, but they have jobs to do also. And so, you know, it's important in having that highly interactive space to have development and engineering bought in early and just to believe what you're doing. And in getting them to believe in what you're doing is to have a framework and to have some structure around it that they get and understand. We're going to come in, we're going to bring the security expertise and guidance, but they're bringing the expertise in their system, and this has to be collaborative because, you know, before starting this, I was doing application security, I wasn't going to be able to work on a CI/CD pipeline. So we got input and buy-in from them to help us build this out. And kind of what that bubbles into is like there's all of these overlapping layers, and so you kind of build this framework sieve, you push your model through it, and out comes, you know, the outputs of your threat model. You choose the pieces that work for you, and you get rid of the pieces that don't. You know, still keep the core functionality and components of it. So ultimately, when you're doing a threat model, you want to build the system, you want to kind of come to terms and agreement on like, hey, what is the thing that we're doing? Are we speaking the same language? Are we looking at the same architecture? So do that, make sure you have that. And then bring in the perspective of like, hey, now we're going to attack this. What is the reason for attacking this? What are the goals? What is my motivation? What excites me about attacking this system, which is going to drive someone to coming up with attacks to get through it? And then that also kind of feeds into like, where do we get the entry points? How do I get ingress into the system? And then how do I propagate through it? So, you know, the last thing is that I know a lot in threat modeling, it is theoretical. Maybe there isn't even a system, maybe it's just an idea, and so like you can't do POC. Or we can't POC everything we come up with because there's not enough time to do that. But have the resources, have the references, do validation when you can. When they start building it, validate kind of the attack trees don't exist or the mitigations that you've put in have been built correctly, and do all of these things together to kind of come up with the proof of concept of like, hey, the threat model actually achieved something here for security. So with that being our approach to threat modeling, we can talk about other pieces of the framework.
Yeah, so before you start to create attack graphs and start to actually threat model your application, you first need to find some sort of authoritative framework that you'll be able to map against it. This isn't a one-size-fits-all approach. What you should do is first understand your actual environment, and then from there be able to map it against like some sort of authoritative framework to be able to follow the pipeline from the beginning to end all the way through the deployment. So with that out there, there's a lot of frameworks. They all have each their own benefits. for the purpose of our threat model, we chose to start our root node on our attack graphs with the OWASP CI/CD top 10. I would be remiss if I didn't bring up cybersecurity. They're one of the actual leaders in this area. They were probably one of the main contributors to the OWASP CI/CD top 10 that we're choosing to start our attack graphs with. But there was a lot of other architecture frameworks out there that went into our threat model and helped us understand the full scope and how we want to attack our environment. And with that said, we found that our CI/CD environment most closely mapped to the AWS deployment reference architecture. And so, like you'll see here pretty soon when we start to actually define our threat models, we have them defined as our stage to make sure we have proper coverage.
Great, thanks, Zach. So,
you're welcome.
Hey, whoa, oh no, we just had that other CI/CD pipeline. What is this CI/CD pipeline? Well, it's yet another CI/CD pipeline. There's lots of them, there's flavors of them, but they all kind of boil down and ultimately end up doing the same thing. And then to Zach's point, we want to have this as an open source reference framework that we can use. So we're going to pivot, and the threat modeling is going to be around this specific framework in CI/CD. Good news is, they map exactly the same. So it kind of rolls up. There's, if you can't see this, it's okay. The legend is a required component of this, and the orange is the required, and the light orange is kind of, hey, you should do this, but you don't have to. So when you see something like this, you're like, oh, that's required? This is free enumeration for a hacker. So you're like, I know that these components are in the pipeline, so now let me go and kind of unpack what this actually means to think of other ways to start attacking.
It's also free information for a security architect as well, for when you're trying to define a secure CI/CD environment.
Because it's required, and these are excellent components. So once you roll all of this stuff up, and if you just roll up all of the other things from the other CI/CD pipeline, you're kind of left with this, which is going to be our pipeline moving forward. We're looking at this from the high level structural element. So you still have local dev, your IDEs, you still have your VCS version control, you still have packages, you still have scripts that are running this, there's still build servers. We get into release artifactories, which is the continuous delivery of this. We have the deployment aspect, continuous deployment, the orchestration that's happening, and then all of the pipeline ends up dumping out into the ocean, and you're running in production, and so that's our pipeline. And don't worry about the dumping out into the ocean part, it's a freshwater pipeline. And so that will be kind of the framework that we go back to for the pipeline, and here's the framework that we're using for attacks.
Yeah, so like I said, our root node in our attack graphs, we need to start somewhere, so we wanted to be able to frame the attack. So what better place to start than OWASP? Specifically the CI/CD top 10. I won't bother going into the actual definitions here, but at a high level, there are obviously 10 of them, and they all contribute to a different piece of the pipeline. There is a bit of overlap, and that's okay. In fact, that's even beneficial, because it'll help frame your mind when you're starting a new attack graph, like you'll see shortly. But starting at the top and working my way right, and then going down, there's, for those in the back that can't see, the CI/CD, the first one is the insufficient flow control mechanisms, which leads us into inadequate identity and access management. CI/CD 3, which is critical, there'll be an attack graph here pretty soon about dependency chain abuse, poison pipeline execution, insufficient pipeline access control, insufficient credential hygiene, insecure system configuration, ungoverned usage of third-party services, improper artifact integrity, and lastly, insufficient logging and monitoring, which should not be forgotten about. So I started with the root node. Obviously, there's an attacker objective in every single hacking attempt, right? So what are the objectives? This will mostly stay the same, but can change for the purposes of this talk. We made it somewhat generic. However, if you are threat modeling your own environment, make it as specific as you can possibly do. But at the end of the day, steal compute resources is one such example would be a crypto miner. Gain a competitive advantage, stealing source code and being able to reverse engineer and understand what's going on to set you apart from competition. Exfiltrating data, that could be anything from customer PII to secrets. Denial of service, which is essentially resource exhaustion attacks. Stealing of intellectual property, and then lastly, extortion such as ransomware. And so then, keeping with the theme of whose pipeline is it anyway, scenes from a hat. So Drew Carey, he has chose these 4 sticky notes on attack trees that we will be mapping and defending against. And yeah.
Great, so scenes from a hat. So there's the OWASP top 10, we're using that. In our threat modeling approach, we have our entries, we have kind of this guidance system that is the CI/CD top 10, and then we have our goals that we've gone over. And so what's going to happen now is that we're going to have the scenario that's kind of pulled out onto the card. A lot of these have overlap amongst them. That's not a bad thing, but don't feel like you're like, oh man, you only did 4. We can do 10, come hang out with us afterwards. We have more of them. We can workshop them with you, but we'll talk about the 4 that we have. So great. Drew has selected CI/CD Sec 4, poisoned pipeline execution. And we want to use the pipeline build system to run illicit code. And then the attack simulation is that a path is accessible that is called to run within the build server. All right, let's see what we got. So just a tiny bit more framing before we move forward. If it's not blatantly obvious, you've seen the framework that we're working on. The red notes that are here are actual attack steps that are happening. Later on, there's going to be some orange stickies that are like manifestations, like CWEs, weakness enumerations. And then the green components to this are the defenses that we would want to build into the pipeline to obviously enhance security and stop these attacks from happening. So poison pipeline execution is like, we have a lot of compute resources that are available in this pipeline. We're talking about building like really complex applications that are going to live and run somewhere. And so, we're sending artifacts in, we're getting artifacts out, and while they're inside of there, there's a ton of CPU processing that's happening, which means there's a ton of resources that are located for us to kind of take advantage of if we want to. So how do we get in there? How do we run this script? What's going on here? Obviously, insider threat, like fine, that happens, it's actually pretty legitimate, and we all know that. But there's, you would want to create a branch, and then you would inject the script to that. There could also be leaked tokens that would get you there. But ultimately there's going to be code that you're going to have and you're going to push it up into the repository that lives somewhere. It can be kind of your own repo, it can be a new branch that you have, it could be kind of a separate thing. It could actually be a callback to a script that already exists, you're just overwriting it there. So I've gotten this script up into the pipeline, and then what I want to do is actually have it called from the build flow. So in the flow that we're talking about, we're using GitHub Actions. And kind of this is like a script that's going to run down and say, hey, pull me in this source code, pull me in this script that I want to use, and I've overwritten the path, and I have this script that's going to dump to the log the credentials to then log into the production Kubernetes system, and I can execute things there. Another interesting thing that happens is that if you have workflows that are in your main branch, as a new developer, I might not have access to that main branch at all. But what I can do is kind of branch off of that, and then what happens when I do that is that these workflows are set up to run automatically just on branching. And so I can kind of branch the main repo, it's accessing the secrets from there, and now I have access to the secrets to dump into the logs, and anyone with read access to a repository can actually look at the logs that are happening. So I'm writing now in the script something that just dumps the credentials from the environment variables into the log that I have access to. This is, again, happening on kind of trivial actions that almost anyone can do because you're branching the repository and then either creating a PR or just kind of pushing something into your own branch that then executes the build functionality and moves forward. So when we start looking at like, hey, how do I defend against this from happening? Like, yes, you can do code scanning, you can do static code analysis, but the two things where that kind of falls apart is like, if you're not explicitly looking at the path where the script has come in, you're not going to catch anything. And a lot of scripts have a lot of good, common, regular functionality that is going to run in the rest of your application, so why would I flag that now? Like, there's not a rule set in SAST that's like looking for this malicious functionality, whatever that is. So the way that we can kind of go around that is that you actually do now start to hard code like paths that you're looking at. I know hard coding paths is bad, but we're looking at specific instances in the repository of where scripts are allowed to live and where scripts are allowed to run from. And so that actually moves forward into approved actions. So another way to actually inject into this is that I can call actions from anywhere in GitHub. So I can say, hey, this is a really cool action. that just takes my container and pushes it into the Artifactory for orchestration to happen. So I could either write that as an attacker and then say, hey, look, this is a really cool thing that does orchestration for you, try to use it. Depending on where you are, like your developers might be like, oh yeah, this script's really rad, this is really easy. But no one's actually doing code reviews on GitHub Actions. Like, you look at it, you see it in the workflow, you're like, oh, you're calling this action in, that's great. The engineers that are doing PRs and code reviews aren't going to catch that this is a malicious action. So it's kind of another example of like how you might be able to inject onto this. But what you can do is then you can also access control actions. And now I have a source repository at my company. These are the actions that we're allowed to use. We have the scripts here. You can only call actions from this repository. And so I've wrapped an ACL around that to prevent you from calling actions from all over the internet. Ultimately, this is a little bit more of a function, of a question actually, around DAST. It's like, so can I look for that, I'm not looking for a specific weakness or like a manifestation of a vulnerability, but can I identify if there's now new unplanned for activity that's happening in my application? So that's more of a thought that we could kind of leave out there. Like, is there something that we can do to validate or build that into what we're doing in the test phase of things? So, ultimately we were able to get the credentials, that gives us access to prod, and then when you're in prod, maybe too much hand waving, but there's a lot that can happen when you're in prod. And so, poison pipeline execution. We've abused the pipeline against itself because of its like very nice, complex, robust computational resources. Yeah.
Word?
There it is.
All right, next concept, scenes from a hat. Zach, your attack vector is typo squatting. Your attack simulation. A developer mistakenly imports a malicious package into their project. The CI/CD falls victim to a supply chain attack via distributed malware. So you can see as dictated outside the pipeline with a little bit bigger of a square, there is a contingency that happens outside the pipeline that you happen to consume. Too bad, so sad. Something happens outside your pipeline that you now need to deal with. So starting the local dev environment, following through the red attack tree, a developer imported a malicious package. The as dictated in the orange weakness above it, never guess it's a package name was the first issue that took place in this. They then committed it to the version control system. Another weakness, there is inadequate code review that's taking place here. No one seemed to notice that pandas wasn't actually the actual library they were trying to use. It then has some unintended consequences of being included in the artifacts. It was not discovered, which then deployed to a forest environment and deployed to production. So taking a step back, going back to the local development environment, and trying to map defenses against that specific weakness that happened in that stage. There are defense mechanisms that you could do to protect yourself against a malicious import. There are a lot of IDE plugins you can put in. There's a lot of security tools, I don't need to name them, but you can implement them to actually stop before you even do any sort of committing to a version control. An alert comes up that prevents you, do not pass go. There are integrity checks depending on what your language you're using. NPQ is a common one for NPM environments. Safety is another library for Python. Continue down and you can find there's integrity checkers for just about every language. In the source stage, probably the same vendor you use for an IDE plugin also has reputation and trust scores. And that is a number that changes based off community feedback. So PHP, for example, had a compromise that happened early in 2023. That specific package number went from a trust score of something very high to very low, and then you can establish thresholds based off the actual numbers defined there. So that will help you in that respect. There are also, similarly to IDE plugins, there are Git hooks you can install that correlate against your software bill of materials that you have. So there could be a diff that takes place and says, hey, we have these approved dependencies and this isn't part of that. Do not pass go. You are not allowed to import this until you reach out to security and say, yo, what's pandas with a Z? This is weird. Moving on to the build phase. There is dependency lock. This is a balance of security. On one hand, you don't automatically want to use the latest release candidate, the latest stable version. You should probably go a couple releases back. That changes depending on other vulnerabilities that may be introduced. But if you remember from earlier, our attack graph is one specific attack graph, and we are trying to defend against that, not the entire company, which is why we do many different attack graphs. So in this case, you could do dependency lock. So wait for other people to fall victim before you. Don't be the first one to automatically update and use the latest and greatest version of whatever it happens to be. There's also container scanning that can take place that could actually identify the malware that's on the containers. That's a defense that you could leverage as well. And then, like I previously mentioned, against the correlation, there's a software bill of materials that you can use so you can actually understand what approved libraries are allowed in your deployment pipeline. The not discovered attack graph, the defense mechanism, essentially a firewall. You can reduce the blast radius. That may or may not have been happening. So how bad is your malware? You're about to find out. Moving down the line, monitoring, alerting. Security operations teams, huge function of security. They need to be able to have the insight to tell if there is compromise happening, which can then kick off standard IR process. So you should check to make sure that's also in place. And then lastly, the production. You know, like I was saying, CD can either be continuous delivery or continuous deployment. Continuous deployment is the goal, but also you want to be safe, right? And you want to protect production because there's a reason your company exists. And with that, there are gated approval checks that could be put in place that can provide you an additional layer of comfort in being able to push something to production. Code review as well. You know, it's kind of sitting before you push to production. Make sure this actual code review of subject matter experts that are taking a look at what you're doing and then approving on your pull requests. And then there's an outbound traffic policy in Kubernetes you're able to implement either through DNS or allowed lists of IPs, which is a daunting task, but at the end of the day, it is still a defense mechanism against this attack graph. And that's it for this attack tree. So I'll go again. I guess I'm Wayne Brady this time. Wayne, your attack vector is an accidental public repo with public information. Your attack simulation. This is a big one. Whew. A mistakenly public repo containing infrastructure as code scripts and Kubernetes manifests accidentally exposed cloud credentials which provided access to resources of a lower environment. The developer fixed their hard-coded credentials but forgot to sanitize their commit history. An overly permissive KMS key discovered by the attacker allowed them to decrypt resources of all environments, including production. So this one's a bit longer, a bit more complicated, and that's okay. But following the kind of the same thinking, starting with the attack graph. Before the attacker even did anything, there were some weaknesses that took place, as dictated in the orange. There was no pre-commit blocking that said, hey, you committed a hard-coded credential. This isn't good. Additionally, once you get to that, a lot of this skipped the local development stage, and the attacker was able to jump right to the source stage because you had a public repository, which again, this CI/CD is insecure system configuration. So there's issue number one. So the attacker, they discovered the public repo and inspected the contents. A weakness that took place here, best practice for Kubernetes manifests, you're supposed to separate the actual configurations of your Kubernetes environments and the manifests separately in different repos. So this was in one public repository, so you gave all the keys to the kingdom early on. Following that same line of thread, they discovered the old commit history. From there, they were able to access the cloud resources of a lower environment. Oftentimes you'll find that production is nice and secure and beautiful looking, but the lower environments are not. They use outdated practices because it doesn't deserve as much attention. The weaknesses that were identified here, less secure auth of the lower environment. There were no logically separated environments as well. The KMS key worked for staging, it worked for development, it worked for production. And obviously there was an overly permissive access key, which was incorrectly scoped. Following the attack tree, the attacker was then able to take that KMS policy and leverage that to decrypt the encrypted values that are stored in Git. If you remember if you remember from previously, we were using GitOps, so most, if not everything, we are storing in Git, which speaks to the importance of securing your source control management suite. Once they decrypted all the environments, including production, they were then able to elevate the privileges in discovering new secrets, which then it was able them to follow the pipeline down to production and connect to the database and exfiltrate data. So already speaking on the weaknesses and now speaking on defenses, going back to local development, there was a lot that was wrong here. They could have sanitized their Git history both locally as well as when they pushed it to the source control management GitHub in this case, which is why there's sanitized Git history in both stages of the pipeline. There's Git hooks, like I said previously, that you can implement. Secret scanning, signed commits, code review, those are all part of your source control management tool that could serve as adequate defenses here. Moving to the continuous delivery and deployment process here, there's a lot that could have taken place. If there was principle of least privilege that was being followed, the blast radius was not nearly as severe. KMS keys for your own separate environment, logging, monitoring, alerting is critical. The actual back-end environment could be separated by different organizational units, which would then prevent you from you'd have to be much more thorough and intentional in creating an overly permissive KMS key if your environment is accurately architected from the beginning. And then lastly, there's a lot of cloud security posture management tools out there. Are you looking at them? Are you actually ingesting those findings and trying to fix them? It's one thing to have the tools, another thing to actually fix the things that need to be fixed. And that's my attack tree.
Great. Nice. Thank you, Zach. Well done. I want you on my team.
Yeah.
What did
fan. I like that.
What did the development team say when you told them to implement all of those things?
How much time do you have?
Yeah. They're like, hell yeah, these are all great ideas.
Yeah. We'll get to it next year.
Okay, great. CI/CD Sec 1, insufficient flow control mechanisms in the pipeline. How do I get something that's not running, or it's in my brain, to running into prod? So attack vector, malicious source code injection, and there's someone in the audience that goes, wait, you did script injection last time. This is source code injection, it's different. We're going to attack a different area of the pipeline. The attack simulation is enter custom code via any part of the pipeline that ends up running in prod. Okay, great. I might be able to see like an argument be made that like maybe I kind of look like that guy, but I'll also give 10 points to anyone who knows that guy's name. 10 points.
Goons don't count.
Okay, so the crux of the issue here is basically like the core beauty of the CI/CD pipeline itself is that you're automating getting code to running into production without anyone intervening. Like that's what people want. They want to get it there as fast as possible. It's kind of what Agile is. Like let's do 1,000 commits a day. And so that beauty of that automation and getting things right up there is also like the attacker's best friend. It's like you're saying that I can get something at any point injected into this pipeline, and because it's automated, it's going to kind of have residual like propagation into production at some point. So that's great. That's awesome. So the core attack on kind of this flow right now is the bypass branch protection that's on here. The things that end up manifesting around this, the orange, is that you have over-permissioned users. I know, we all hear this and say this a lot, but it's really a thing, and it's like, there's humans in the loop all over this. We're assigning roles, it's not automated, we're bad at it, we're bad at setting it up, and we're bad at cleaning it up, we're bad at taking it down. And so that over-permissioning of users is a challenge. The other thing is just a misconfiguration. And so you're like, well, wait a second, you said that there was going to be overlap between some of these pipeline attacks. Well, there you go. Zach was just talking about system misconfiguration. This is one of those things also. So in your Git repository, there's this great thing called branch protections, and it prevents people like me, junior engineer, it's my first day, I want to be awesome and commit stuff and commit right to main, and then that ends up running in production, and you're like, oh, crap, we shouldn't have allowed that to happen. So branch protections kind of set rules around who can actually merge with main and then push into production. But if it's not there, or if it's set up incorrectly, then you can get past them. And so the ways that I'm able to then get things into the source is fine. I might be an insider, I might write some code that's just malicious and like somehow get it past someone. Well, if you're not doing code reviews, if you're not doing pull request reviews with peers, then I can write anything I want and have that push too. So that's kind of like, yeah, all right, fine. We need some manual human in the loop type stuff for that. The other thing, write malicious dependency. So someone might not even know that this exists at all. Like I might write something that my project wants to use, like, hey, I'm going to do this really cool string sanitization. I'm going to write my own library for it, and I'm going to put it into our own inside Artifactory, and then I'm going to call it later in the build stage. But I'm going to first like make my own branch or my own GitHub repo that stores this and does this, and I'm not going to tell anyone about it. We're going to go into the code review and be like, this thing's dope, look at this sanitization that I'm doing here, and just ignore the rest. Again, just like we weren't doing code reviews of actions, we're not going to be doing code reviews of dependencies either. So that's how I'm kind of injecting into all of this. And then if these things are misconfigured or if my user has too much permissions, I'm able to get it into source, which then again, then propagates all the way through. Like once it's sitting there in main, no one's looking at it again. And it's getting compiled and built and deployed with all of the great things that we've talked about and how that happens. So then skipping, there's actually a whole other side to this that like you can ignore that altogether. If you're running code, if you're using AWS Lambdas and you just have code up there and I get access to that, that means that I'm actually hands-on just editing code that's running in prod. So I've bypassed everything. I really don't even need a pipeline at that point. I'm just editing the code that's running on your system. Same type deal with tokens of getting into Kubernetes and pods. I'm then live on a production system. It's kind of anything goes at that point. So defending these things, let's see, audit enable protection configs. So set them up, set up your branch protections, and look at them regularly to make sure that the switch doesn't somehow, single event phenomenon, the setting has changed. Do peer reviews. Yes, it's human, but do it, you learn. We build trust and we're a team. Static analysis, great, a lot of great stuff that does that. And then rules kind of harkens back a little bit to like the configurations, but it's rules specifically on a branch of like who can push, who can merge, what level permissions do you need for that. Supply chain ACL for the Artifactory, like use an internal one and review everything that's in there. Don't allow me to call to any GitHub repo on the internet. Don't allow me to call from the public Docker registry. Dependabot can check things for the vulnerabilities. S-bombs, man, these are hot now, right? They've been hot for a couple years, actually. But software bill of materials. These, like, if you're using a VCS, this is probably packaged and happens there. Like, you have this exists. So just reference this, check it. Use the S-bomb and reference it back to what your ACL for what packages you're allowed to use. And then tags and hashes, set these up. Don't use latest, because then I can just overwrite something to latest, and check them. If I have, we have an ACL that you're using this package, well that has a hash, and so when you pull in all the packages to your build system, check the hashes there also. And then check the hashes of the things that are running in production. All of this exists, and we can use it, and we will. So ultimately, access to the cloud, do some change control, have cloud release management, don't allow live editing of Lambdas that automatically are running, and then everyone's favorite, user access control. Great, Zach, let's get out of here.
Woo, yeah. Themes and takeaways, lots of IAM. Lots of user access reviews, overly permissioned, service accounts, we really didn't even reference them. That falls into this as well. Pretty critical. SCM, GitHub was already important, that hosted all your code is becoming more and more important. So be sure to actually take a look at GitHub and make sure it is properly secured. Not just branch protections, but also GitHub teams and provisioning. You should implement that into your OICD provider, OIDC providers, such as Okta or whoever Okta chooses to purchase. Know your CI/CD environment. Attackers are already there.
Cool. Yeah, what are my takeaways? So I think we're building. Everyone else is out there like building really cool things that they're really proud of, and they're building really like advanced, awesome, cool widgets that are cool. But you don't need your pipeline to be the latest cool thing. Make your pipeline something that's reliable, use the technology that exists, use trusted tech stacks, and then use the documentation. When you have an actual mature tool, there's a section in there that says these are the security best practices. When you're threat modeling, read those and bring them in and say, hey, are we doing these things? And if you're not, you can create an attack vector based off of that gap. Integrity checking are favorite, SBOMs, dependencies, doing access and like allow lists, these are huge. The actions, the dependencies, the scripts, knowing your environment is part of that. You know your environment, you know what's allowed, so you can control what's there. And then, back to everyone is building cool stuff. Everyone's really good at building cool stuff. Engineers and developers honestly love security. They're hyped when we talk to them about this. And they're the experts on the system. I am not. I can talk to you about security. I didn't know about pipelines a couple months ago. And so going to them, using them as a reference, building that relationship too, kind of fostering that teamwork, that's fun. So that also ends with threat models being mutually beneficial, and if you aren't threat modeling, you should be. There's some references for later, looked at that on the recording, and thank you very much.
Thanks, sir.